Hi. This week we're going to look at waves, and we have got a few video lessons for waves. In this one, we are going to focus on three things: path difference, phase difference, and interference. In particular, how does path difference give rise to phase difference, and how does two waves with different phase interfere and combine together and give us constructive and destructive interference. Let's look at what path differences and phase difference is first. Path difference is difference of two paths in meters. If you haven't gotten this down, you should write it down in your notes. What does that mean? That means that if I have a source X and Y, maybe these are two loudspeakers, and I've got a microphone in here, which is a receiver, you have got two paths, from X to the receiver and Y to the receiver. Let's say that from X to the receiver is 20 meters, and from Y to the receiver is 50 meters. The path difference will be 20 minus 15, which is 5 meters. So path difference will be 20 meters minus 15 meters, which is 5 meters. It's the difference between the paths. Okay, so this is what we called path difference. It's the distance between the two paths that the wave has taken. Okay, so this is completely, this relates to phase difference, but you don't need to have path difference to have a phase difference. Phase difference just means that it's the difference of where you are at the wave or the cycle. For example, if I have a wave like this, this is one cycle. If I have A, B, C, D, E, between A and E, the phase difference is entire cycle. Between A and C, the phase difference will be half a cycle. Between A and B, the phase difference will be quarter of a cycle. But each cycle, because we know cycle is a circle, each cycle is 360 degrees or 2 pi. So between A and E, the path difference will be 2 pi because it's an entire cycle. Between A and B, the path difference will be pi. And C, the path difference will be pi because it's half a cycle in here. Or we can say that it's 360 degrees or 180 degrees because we model a cycle like a circle. So let me now link between path difference and phase difference. If you have two sources, such as two loudspeakers, or in optics, it could be Young's double slit or diffraction grating. If you have a 20 meter path in here and 15 meter path in here, let's say that this is just an example. Of course, different waves will be different, but in this example, I will say that the wavelength is 10 meters. There's very little wave that's 10 meters. Maybe you can get some radio wave that is 10 meters, but in EM waves, there's not very waves that's 10 meters. But I'm just giving you an example, okay? So, how many waves can we fit into X and O? Okay, 10 meters, that's 20 meters. I can fit in one wave and two waves. All right. Now, how about Y and O? If the wavelength is 10 meters, I can fit in one wave and a half. Let's pan it out here and see what is going on in here. So, is this between X and O? This is between Y and O. Between X and O, we have got one wave, two waves, because each wave is 10 meters. And between X and O is 20. Between Y and O actually is shorter than X and O. So I actually start here. Okay? So I've got one wave. Nope, I don't start here. Start here. I've got one wave and two waves. See, this is 50 meters. And the wavelength is 10. So, how many cycles can I put in here? That's one cycle, that's two cycles. Between Y and O, that's one cycle and a half. Why? Because the wavelength, it is because of two things. The path and the wavelength. Firstly, let's look at the path difference. The path difference is 5 meters. Why? Path 1, path 2, the difference is 5 meters. Okay, now, if I just look at these two waves, how far ahead is this wave compared to this wave? Okay, let's look at our wave in here. This is one cycle. How far ahead is this wave compared to this wave? I have missed half a cycle in here, half a cycle in here. Do you see that the phase difference between these two waves is half cycle? If the phase difference between these two waves is half cycle, that means that this is, the phase difference is pi, or 180 degrees. Okay? How about the path difference? The path difference is 5 meters. Let's express this in terms of lambda. Lambda itself is 10 meters. Lambda is wavelength. So in here, the path difference is half lambda. Why? Because it's 10 over 5. So our path difference is half lambda. Do you see that if path difference is multiple of half lambda, the phase difference is always pi or 180 or multiple of that? What does that mean? When you have phase difference of pi or 180, you see this bit add up to this bit. If this bit is -1 plus 1, it evens out. It cancels each other. Let's look at this bit. The top cancel the bottom. The top cancel the bottom. So these two waves coming together is going to give us destructive interference. These two waves coming together is going to give us destructive interference. Let's recap one more time. Firstly, how do you find the path difference? The path difference is the difference between the two paths the waves have taken in meters. Path difference is very, very useful to express in terms of lambda. How many lambdas? One wavelength, two wavelengths, half a wavelength, 1.5 wavelengths. Why? Because these two things, how many lambdas, how many wavelengths, is going to tell us where the phase difference is. If the path difference it is at the end of the cycle, which is 2 pi's, 4 pi's, and so on, 6 pi's and 8 pi's, they would have constructive interference. If they are at 1.5 pi, 0.5 pi, and so on, they will be at disruptive interference. So let's look at, let's write down what is our point in here. So when the path difference is the multiple of lambda, then, for example, 1 lambda, 2 lambda, 3 lambda, 4 lambda. Let's recap what path difference is. It's the differences between the two paths the wave has taken. Remember, that's a number. you need to put it in terms of how many lambdas, how many wavelengths are there. For example, if there's 20 meters difference and the lambda is 5 meters, then it's 4 lambdas. Okay? Okay, the phase difference will be multiple of 2 pi, which is 1 cycle, 4 pi, 2 cycle, 6 pi, which is 3 cycles. If the phase difference is this much, then they will add up. When they add up, they will have constructive interference. That doesn't mean that the wave is going to double. That just means that the two waves are going to add up. Okay, the amplitude and the displacements are going to add up. When the path difference is a multiple of half lambda, for example, half lambda, 1.5 lambda, 2.5 lambda, 1.5 lambda is 3 over 2 lambda, and 1.5 lambda is 5 over 2 lambda, and the phase difference will be half a cycle, pi, or 3 pi, which is an hour and a half cycle, or 2.5 cycle. If they do that, the crest meet up with the trough like this, and they will cancel each other. Doesn't mean that they are completely cancelling each other. For example, if this is 2 meters high, this is 1 meters high, the eventuality will be, it's got 1 meter, because it's 2 minus 1, okay? It doesn't mean that it's 0, that just means they're cancelling each other out. And that will give us destructive interference, okay? Alright. Alright, so let's put this into practice. Let's look at our slide 2 of the PowerPoint. Slide 2 of the PowerPoint. It says, what is the phase difference between 2 points 0.16 meters apart on a progressive sound wave of frequency of 256 Hertz? They have given us the speed of sound, which is 330, okay? And frequency of 256. So, if you have a speed, if you have a frequency, what can you actually get? B equals F lambda, you can actually get the wavelength of the wave. Let's do that first. The wavelength of the wave will be 330 divided by 256. So 330 divided by 256 is 1.289 meters. So that's the wavelength of the wave. So the wave will be 1.289. They are saying that point A and point B is 0.16 meter apart. So how far apart in terms of cycle is it in the wave? Really easy. Will be 0.16 divided by 1.289 cycle. So point B is put that into the calculator. 0.16 divided by 1.289, that will be 0.124 cycle ahead. That means that point B is 0.124 cycle ahead of point A. 0.124 is around 1/8 cycle. Okay, if you divide 1 by 8, it is 0.125. Okay? So if I divide the wave, which is almost true, if I divide the wave into, this is 4s, 1, 2, 3, 4, and I divide it again, this is around an eighth. This is around an eighth. Okay? Alright, so if this is an eighth of the cycle, remember each cycle is 2 pi. So if so point B, in terms of pi, how many cycles is that? Each cycle is 2 pi. So this 0.124 times 2 pi will give us the phase difference. We are not doing it in terms of cycle now, we are doing this in terms of pi. So in here, this is going to give us 0.248 pi, which is around 0.25 pi, which is pi over 4. Hence the answer. This is how you turn from phase difference to path difference. Alright, what I want you to do now is pause the video and do question 2, and we'll come back to it. Okay? It's very, very similar question, but I want you to try it. Okay? We'll come back to it. Alright, please try question 3 as well. If you don't understand this, leave in the comment below. Okay, question 5. This is going to be slide 4 of the PowerPoint. Let's try for question 5 together. We've got two sources, S1 and S2, and this is projecting onto the loudspeaker or microphone over there. It says that we are getting maximums at W and Y. W is here, this is maxima, this is maxima. When you have maxima, you have contractive interference. When you have minima, X and Z, this is disruptive interference. What do we know? When you have maxima in Y, the phase difference is 2 pi, because in here the phase difference is 0 and the path difference is lambda because it's constructive. When you are at minima, this is the phase difference, this is the path difference. Ooh. Right, when you are at minimas, the phase difference in here is pi, and when you're minima, the phase difference in here is 3 pi. Path difference is half lambda, and this is 1.5 lambda. Why? Because in here, when you are minima, that means that the crest matches the trough. That means that the wave is going to be half a cycle ahead of this next wave. Okay? Right, anyway. So they are saying that which one of the following is the correct expression for the wavelength of the sound? The wavelength of the sound is going to be equal to the path difference when there is the first maximum, because the path when the path difference is lambda, it will give us the first maximum. So this is when you are at the first maxima, path difference is lambda. This is a coincidence. Second maxima, the path difference is 2 lambda. So don't always think that path difference lambda, yes, this is going to be my constructive interference. No, constructive interference is path difference is never just equal to lambda. Okay? Remember, what point is that? When the first maxima, the path difference is lambda, so we can actually calculate lambda within that. How do you do that? From this point, how do you get path difference? Okay, let's actually map out the two paths. This is the first path, which is S2 to Y, path number 1, and this is second path, path 2 to Y. So this is longer than this one, so I do S2Y minus S1Y. And the answer is D. Well, it's going to give us a negative number, but It's going to be fine. So the answer is D. S1y minus, oh, incorrect, because they actually did this as 1, this as 2. So this is S1y minus 2y, because S1 distance is longer than S2. Okay? All right. Moving on to the next question. Please have a read of the next question, pause the video, and we'll go through a little bit of that. Hi, welcome back. So we're going to do question 6 and question 8. I'm going to give you a lot of hints in question 6, but I'm not going to, slide 6, I'm not going to give you any hints in slide 8. If you're still struggling, rewind to the earlier part of the video and you'll understand more about this. I appreciate question 28 is more about percentage uncertainty and percentage error, which we're going to include in a different video. But in this situation, what I want to focus on is path difference and phase difference. So, for example, and I'll talk through it. And if you don't understand percentage uncertainty, percentage error, we're going to go for it another time, not this time. But I'm going to go through it really quickly, but we'll focus on path difference, phase difference. 28. You've got speaker 1, speaker 2. At A, we have got central maxima. At B, we've got first minima. At C, we've got first maximum. So, the question A1 suggests a reason why is it difficult to locate position C precisely. B is in minima. What can you hear at minima? Why is it difficult to locate that position? A2. Why is it difficult to measure a position A and speaker evenly? So A is in the middle of that. Is it difficult to find what the center of that is? We are 3D. Is it really, why is it easy? Why is it difficult? Is it the same level? Okay, so B1, calculate the wavelength of the sound waves. Wavelength, what do we know? We know that first maxima, the path difference is lambda. Okay, so how can we calculate path difference? Path difference we calculate by the difference between the two paths. So we know that lambda will be the difference between the two paths, which is 0.61. This is what I want to focus on. Whenever you see a question like this, now you know that path difference is our focus. Okay, we're going to skip over question B2. We're going to include it in another video. But the question C, we're going to look at it now. It says that calculate the speed of sound from this data and make an estimate of uncertainty. We have got V equals F lambda. We have got lambda, we have got F. So, in this situation, we can calculate V, which is 560 times 0.61. So, this is the easy part, which is 342. How do you calculate the plus or minus something? When you plus or minus something, this is the absolute uncertainty. Okay? So, in this situation, how do you calculate percentage uncertainty? Oh, the equation between absolute and percent uncertainty is absolute uncertainty over the value. In this situation, the value is 342. So you have got individual uncertainty multiplied together. How do you add them together? You can't add absolute uncertainty, you have to add percentage uncertainty instead. So we need to turn absolute uncertainty of this one and add absolute uncertainty of this one into percentage uncertainty. So percentage uncertainty of F will be 30 over 560. Percentage uncertainty of lambda will be 0.02 over 0.61. Add these two up together will be the percentage uncertainty of V. And then afterwards, you need to turn it back to absolute using this equation. And your value will be 342. And after that, that will be the answer here. Okay, this is C. I'm going to talk about D. The student now reverse the connections of speaker 2, but keep the connections of speaker 1 unchanged. State and explain the effect this will have on the signal measured in A and C. That means that this is the signal from signal 1. Originally, this is signal from signal 2, but instead I'm reversing the signal into this instead. If I add this to this together, what am I going to get? We're going to get a minimum. So, because the phase difference is 0, that means that this matches up with this. Central maxima will turn into central minima instead. And first maxima, with the same logic, will turn into first minima instead as well. Because it is one wavelength ahead. So this is one wavelength ahead of this, because the path difference is lambda. Okay, what I want you to do is try these two questions. The answer is in the marking scheme is included in the PowerPoint. So please try these two questions and come back again for another episode of Waves. Okay, bye.